Ørsted observed that the direction of the magnetic field depends on the direction of the electric current. The direction of the field is given by the right-hand grip rule, actually through the use of vector calculus and the Biot-Savart law, which we'll get to next unit, but this handy mnemonic gives the same results. Orient your right-hand thumb in the direction of the current, and don't do this with real wires that have current in them, right? Because what if there's a break in the insulation, you could get hurt. But just visualize this. And pretend you're gripping the wire, hence the right-hand grip rule. The magnetic field follows the path of your curved fingers. So you can see as you curve your fingers around, that's what the magnetic field is also doing. Then to find the magnetic field at any point on the concentric circles, you draw a tangent line to the circle. The tangent line points to the direction of the magnetic field at that point. So over here, the magnetic field is going like this. Here, it's kind of going into the page. Once again, it's hard representing 3 dimensions on a piece of paper. But let's look at this one. There you go. So at any point, you can see how the magnetic field is pointing. There is no component of the magnetic field pointing towards or away from the wire. When you have a current circulating around an iron core, a magnetic field is created, and the device is called an electromagnet. This is an industrial electromagnet, and when the current is turned on, it picks up metallic objects. Metal scrap here is being attracted from the ground to the electromagnet. What would happen when you turn the current off? Well, the magnetic field would go away and all the scrap would fall down. So what you would do is pick it up in one place, move to somewhere else, and then you can dump it by turning off the current. Another difference between electric and magnetic fields is that we can normally understand an electric field very well on 2-dimensional paper. The electric field is of course 3-dimensional, but you can easily represent it in 2 dimensions. But as you just saw with Ørsted's experiment, the magnetic field is looping around the wire, so magnetic fields need to be shown as 3-dimensional to be understood. Somehow we need to show this 3rd dimension on our paper. So we can do left and right pretty easy. We can do up and down. How do we represent the 3rd dimension on a piece of paper? This is the standard convention. Picture the magnetic field line, which is a vector with magnitude and direction, like an arrow. The head of the arrow is the direction of the field, and the tail here would be where the field's coming from. So if the magnetic field is into the page, you'll see the tail of the arrow. And the arrow, that's kind of the fletching of the arrow stuff in the back, so that looks like an X. So when you see this, this is a magnetic field into the page. And actually, if you want to do electric fields, you can also say that's an electric field into the page. It works. If the magnetic field is out of the page, you see the front of the arrow, which looks like a dot. So you put a whole bunch of dots together and you have a magnetic field coming out of the page. What if you have a current carrying loop? What would the magnetic field look like? You use the right-hand grip rule, right? You put your thumb in the direction of the current, which is that way, and you grab the wire. When you curl your fingers around, you see that inside the wire, you're going into the page, so that's X's. You continue to curl your fingers, and on the outside, it's coming out of the page. So the magnetic field will be dots outside the loop. And notice for this would be a little harder to orient your hand, but it gives you the same result. So you can place your hand anywhere on the loop.